So let us have a brief introduction about what are the parabolic equations. The parabolic equations are employed to characterize time variable problems. So time variable problems means the the variable which varies with respect to time. So that kind of equations are called transient equations. So these parabolic equations deal with transient problems. Parabolic equations are derived using finite divided difference for partial derivatives. It utilizes the same concept which we learnt in the previous sections of this chapter. Second, the elliptical partial differential equations were bounded in all relevant dimensions. However, parabolic partial differential equation considers change in time as well as space. So in mathematically it can be represented. So x parameter represents a, space parameter and t represents the time parameter. So thus parallelly it deals with the time as well as space problems or space. Now there are temporarily open-ended problems as their time variable as they are time variable in nature. The solution to the parabolic partial differential equations involves number of new issues related to the stability. So that stability matter, so you are going to learn in case of control systems and in case of vibrations, so that things, so you will learn in later stage. So just I am stating this as relevant to the problem. There are two ways to present fundamental solution approaches, so that is explicit and implicit way. So here we are dealing with only explicit kind of things. The second derivative in space is represented by a Laplace equation by using central finite divided difference method. So this central finite divided difference method, so we have not learned it. So we are going to learn this in forthcoming units. So I will explain in detail. Just you remember that wherever we have used this finite divided difference method, so you recall these things there and relate to these parameters. The temperature T is a function of space. Just now we have discussed there is a function of space and time, because all these problems deals with respect to variation of a particular field variable with respect to time of a metal rod exposed to two different temperatures at each end can be found by using heat conduction equation. So as you might be familiar with the some simple examples of say a rod or a fin. So this fin is subjected to temperature where it is fixed. So usually it has high temperature in case of a cylinder, and this is subjected to high temperature and this is subjected to atmospheric temperature. So here the temperature flows across this fin, or the heat will be emitted from the fin, so from the surface as well as from the tip. So the temperature distribution, the flow of heat across this fin varies with respect to time. So at a T is equal to 1 second, what is the temperature? At T is equal to 2 seconds, what is the temperature? Likewise, with respect to variation in time period, so what will be the status? What will be the state of temperature at different time periods. So that we are going to compute by using these parabolic equations. So where alpha is equal to k by rho c, daba square t upon daba x square is equal to daba t upon daba small t. So here it is a differentiation with respect to space parameter and with respect to time parameter. The above equation is a heat conduction equation which requires approximation for second derivative in space, and see here second derivative in space, so relevant to the x parameter, and first derivative with respect to time. So let us discrete the bar or a rod of length L, which is divided into n plus 1 nodes. The time is similarly increment into a time step of delta t. Hence, Tij corresponds to temperature at node I. So that is represented with the help of diagram. So here x is equal to I into delta x, where t is equal to j into delta t. So this same concept we have used in elliptical equations in previous case. See here also. So it means that x is deals with x direction and temperature deals with y direction, j node, x and j. Here you can see, so this is the line. So along with this line, so there will be a temperature variation. So that temperature variation is dealt with respect to delta x, and parallelly there is a one more axis. So this axis will be referred as, for example, y-axis, and it is represented by j parameter. See here. Here j parameter. So this increment is represented with delta t time period at j is equal to 1. So thus, so this represents the temperature profile. Temperature profile at j is equal to 0 or at time period t is equal to 0. So this is the temperature profile. And so at an interval t is equal to 1, so this is the temperature profile, and we have to compute the temperatures at delta x intervals, as well as, so we have to compute the temperature at t is equal to 0 second, t is equal to 1 second, and t is equal to 2, 3, 4, and so on. Now here delta x is represented by L by m. From equation, from previous equation, so that is alpha into daba square t upon daba x square is equal to daba t upon daba small t. From this equation, so we can write the finite central divided difference approximation. Again, we have not learned this central divided difference. So this we are going to learn in the next chapter. So here, the same thing. So this diagram, this is the 3D diagram or two-dimensional diagram. So this diagram is represented in 2D form as this. So this represents, this is the one line. So here, so the temperature, so if you want to predict temperature at Ij, and its increment is, the next interval is I plus 1j, and here I minus 1j. So thus, so this represents the temperature difference between these three nodes. By using these two, so delta x1 I can call delta x1 is equal to T of Ij superscript j minus T of T I minus 1j superscript j difference of these two divided by h interval. That is delta x. And similarly, if you want to take, so this is delta x2 equation. So as we have discussed this, delta x2 is equal to t I plus 1 j superscript j minus t I j. So on simplification, this equation already we have derived this. So using central divided difference formula, so we got this equation, and delta x square represented in previous equation by h square. And these are the different locations of temperatures. So that is location 1, 2, 3. So relevant to this, so from this diagram, so we have derived this equation, and the similar equation we have derived in previous chapter also. Sorry, the previous section of same chapter. Now here j is the node number along with the time interval. So this is the time interval. The time derivative on the right hand side is approximated by forward divided difference formula. Here we are using two concepts. One is forward divided difference method to find the value of delta capital T upon delta small t, or dabba t upon small dabba t. And for this, so we are using central divided difference formula. Here you have to remember two things. For second derivative, we are using central divided difference formula. For first derivative, so we are using forward divided difference formula. By using this forward and central divided difference formula, so we are determining the relationship. See here, so this is the relationship used for predicting dabba t upon dabba t. See here, t of I j plus 1. So this is the j plus 1th interval, and minus t I j of superscript j. So this is same thing divided by, so this is delta t. So like this, so we are utilizing time space in this direction. Sorry, space in this direction, space variable, so that is x in this direction, and then so time derivative in this direction, or time interval in this direction. So thus, so parallelly we are dealing with x direction as well as y direction. In y direction, so we are dealing with temperature, time, and in x direction with respect to space. So thus, so we are dealing with this, and by using central divided difference formula or concept and forward divided difference concept, so we are obtaining these two equations, equation 2 and 3. So these 2 and 3 equations are used for predicting a field variable. Now you substitute these equations, so in the equation, so after substituting this and on simplification, so you will get temperature at node I, so at new location. So that is location, I will tell you, this is the new location. So we would like to predict the temperature at this location based on the information available here. So this is, so just you remember this, based on this information available, so we are going to predict the temperature at t is equal to say 1 second. So here j is equal to 0, j plus 1 is 1 at second 1. So what might be the temperature at this location? So that we are going to predict. So here what is expected here? So we need to know the value of this, and value of this location. Based on these three locations, so we are going to compute the temperature at time period 1 second or 2 second, 3 second. It is based on that given parameter. So likewise, so or this concept is used in used in this method. Based on this, so we are going to compute a temperature. So this is a relationship, so which is used for computing the temperature at new location, and where so lambda is alpha into delta T by delta x square. So it is alpha, alpha is equal to K by rho C, and delta T represents increment in time period, and where delta x is so increment in space. So these things, based on that you can calculate lambda. Once you will know the lambda, so we know what is the temperature state at this location, temperature state at this location, and temperature state at this location. So by knowing these temperature states, so you can compute what is the temperature at new location, or temperature for internal nodes of the rod for time period J plus 1 in terms of temperatures of current time node J. So this is the theory